version of surface area, surface integral, I should say, and that is this type. And now I can tell you what the flux is, and the guy I call the flux is this fella. And this, for some reason, is a biggie in physics, but essentially we're doing the double integral over a surface of a vector field F, and that's the way it's going to be written. And we are being interested in the surface is that cone, which is essentially the blue bit, sandwiched between a z equals 1 and a z equals 2. So I don't know how, oh, I can make it bigger, right? Sure, I can do that, yeah. There, does that help a little bit more, maybe even more? How much? Yeah. Can you see the blue is the surface, but the piece of the surface I'm talking about is that bit there, right? It's sandwiched between z equals 1 and z equals 2. So that's the surface, right? And on that surface, there is every single point on that surface, there is a vector function being applied to it, right? So at any given value of x and y, there's a vector associated with it. And we're going to add the whole darn things up and essentially get the flux, which I believe represents the work done in moving through that vector field with that surface. Not being a physics guy, that's the closest I can do it to. So I'm going to now nip over and show you how to do that particular kind. So I can bear with me for a few moments. Here we go. So if you want to get the double integral over a surface of a vector function ds, here is our guy. It's a double integral over an area D of negative P d g by dx, negative Q d g by dy plus R equals 0. And let's try and tell you all the pieces of that puzzle. Your surface is z equals g of x, y. So when you're doing the differentiation with respect to x and y, it's the surface. D, oh, I've already said that. D is projection of the surface onto the xy plane. You can actually project it to any of the three planes, but xy plane is probably the easiest one to do. And F is P, Q, R. F is your vector field, right? So there are lots of components here. There's a vector field, there's a surface, that's this guy. That's basically surface S. There are restrictions on it, so it's not just that guy, it's that guy, in this case sandwiched between two things. This double integral, dx dy. Now sometimes when you do this double integral, it ends up being like x squared plus y squared kind of look. If you see that, won't you probably do polar on it for calculation purposes? But right now we're just going to pretend they're all x and y, and then we'll see what we get. Now in the question 6 that I just showed you, you have a surface described by z equals the square root of x squared plus y squared. So that means you've just told me who g of xy is. I'm going to write it in that format because it just makes life a little bit easier. But it's also sandwiched between z equals 1 and z equals 2. Right? But that's the main guy, and that's just coming later. If you project that shape, the picture that we had, you get a guy that looks like this. Got one here and one here. So if you made z equals 1, you get a circle, radius 1. And if you put z equals 2 in here, you get a circle, radius 2. I know that picture's missing, but you remember the cone that we showed you that was sliced? If you looked at that cone vertically above, wouldn't you see this donut shape? Right. Cut at z equals 1 would get you the inside circle. A little bit higher at z equals 2, you get the outside circle. So this is all the major stuff with one extra thing. And the vector field is negative x, negative y, z cubed. Double checking that. Negative x, check, negative y, z cubed. So that's my p, that's my q, and that's my r. So if I put all those pieces together, I should be able to turn this flux, this surface integral, into this normal, more normal looking double integral. So here goes. The surface integral, which is this fella, is equal to a double integral, negative p dg by dx minus q dg by dy plus r dx dy. Now, looking at my region D, would you agree that that lends itself to being polar coordinates? Would you agree if I tried to do that x from here to here and y from here to here, it would not be a pretty sight. So I am going to do r equals 1 to r equals 2. Since it's is it a complete one? Yes, complete circle. So from theta to 2 pi. There's my r dr d theta, basically, that's that transferred. Now, I'm going to keep these as x's and y's until we see what we're going to get. So this is going to be a right mess. So the negative of p is just x. And if you differentiate this with respect to x, you get 1/2 x squared plus y squared to the negative 1/2. Okay. Second term is going to be this guy. So it's going to be plus y times, and nobody noticed my mistake, times 2x. There we go. So it's going to be y. Differentiate this guy with respect to y. You only get 1/2 x squared plus y squared to the negative half times 2y. And you're also going to get a plus an r, which in this case is z cubed. Now, if I'd thought this through, I would have started way over here. So that guy, that guy, that guy, that guy, basically you get x squared, and this guy goes downstairs, you get that one. And if you do this one, you get y squared eventually over that one. And then I have a z cubed. Everything has to be turned into x's and y's, right? I can't have any z's left over. Who does z get replaced by? What do I replace my z with in terms of x and y?
Would it be the root of x squared plus y squared?
Yep. I'll just write it like that. R dr d theta. Well, it's looking a little bit nicer. Still got a fair distance to go. Okay, I want to convert everything here into polar. Certain things turn into polar much nicer than other things. Would you agree that this guy is just r cubed? I'm going to have to work on these two guys for a minute. They share a common denominator, don't they? So couldn't I call that x, well, can I write it here? Couldn't I call that x squared plus y squared over a square root? What does that simplify down to? Well, x squared plus y squared on the top and the square root of the same thing on the bottom, isn't that just x square root of x squared plus y squared, which isn't that just r? Are you happy about that? Ends up being r. Or if you like, r squared over r, which becomes r. That makes more sense to me. Are we good with that? Right, now, almost done. These are separable. And I'll multiply this out. I believe you get r squared plus r to the 4. And then I have a theta from 0 to 2 pi. Don't have anything, so call it 1. This guy is 2 pi. Oh, yeah. What's the answer to this thing going to be? I was trying to look up the answer, but it's not there right now. Okay, this is going to be 1/3 r cubed plus 1/5 r to the 5, evaluated at 1, evaluated at 2. So times 2 pi. So I'm going to have something times 2 pi. 2, 4, what's that? 8/3. Take away 1/3. You got that guy. 2, 4, 8, 32/5. Take away 1/5. I should have done that in one big go, but never mind. All of that guy. That's just not right. In brackets then, 1/3 times 8 plus, in brackets, 1/5 times 2, 4, 8, 16, 32. Okay, that's the first guy. Take away a bracket. It's just a little bit easier. It's going to be 1/3, add 1/5. And hopefully that comes out as some decent fraction. Okay, 128/15. So I get 64/15 pi. Okay, time to find out what the answer is. I'm halving that instead of doubling it. 256/15 pi. Okay, I almost got to the end, right? It's a doubling of the top. And for fun and giggles, it's negative. And
I have a question about the negative.
yeah, it's to do with the orientation. So I'm reading the question. It says evaluate the surface integral for the given vector field, orientation surface S. In other words, find the flux, which was talked about. For a closed surface, use the positive outward orientation. Yet they made it negative. So why? They're saying that that shape is a downward orientation, right? So the shape we've got looks something basically like this guy, right? That napkin ring. According to them, it has a downward orientation. I don't know why is the short answer. Evidently it is. The way they phrased the question was, for closed surfaces, use positive outward orientation. So why would that be? Why? What evidence is there that this is pointing inwards? Because inwards would be negative and outwards would be positive. Is there anything in that story that makes me know that it's pointing one way and not the other? And all they say in the notes I have here is that it's pointing downwards orientation, so it's negative. I'm doing little funny things with my hand here. Right hand rule. It may be something to do with the right hand rule. You got a surface that's pointing down the way, and the vector fields. Nope, that doesn't make sense to me either. I don't know. I don't like not knowing, but I don't know why. With the evidence they gave me, I can't tell why that would be orientated in a negative direction. Did someone got their version in front of them and did they pick up something I missed? Because there's nothing that I can say. The good news is if it doesn't work with the first one, can't you change it to the second one pretty quickly? And when you become an engineer, which I definitely am not, this is kind of proving it, you will say, oh, you can tell just by looking at the surface whether it's a negative or a positive. For me, I can. If there is a test, I don't know it. How are we doing with that one?
I have a question at the very beginning when you were setting up the integral.
Sure.
Where did the negatives go? The negative p, negative q.
Negative of negative x became plus x. The negative of negative y became plus y.
Ah, okay, I see. Thank you.
I wonder if it's the vector field that tells me it's negative, but then there are two negatives and one positive, so that doesn't help. No, still don't know. You know, that's going to bug me now. How do you tell by looking at a surface whether it's positive or negative orientation? Okay, let's do another one. Version of question 7. We're being asked to find the usual flux, which is that guy. And what do we know in this times? Okay, at least this one, they told me it was orientated downwards. Yay, just tell me. And then I noticed like a negative on it, right? Orientated downwards, negative. Orientated upwards should be positive. You told me, great. My life would be so much simpler if you could just do that. So we have a y, a negative x, and a 4z. That's fine. The guy that we're talking about, the surface S, is a hemisphere, and its equation is x squared plus y squared plus z squared equals 4, and z is greater than or equal to 0. If you're talking about a hemisphere, they're talking about half a sphere. And in this particular one, because z is greater than or equal to 0, would you agree it's the top half that they're talking about? Now, if you take that and you project it onto the xy plane, can you see that you now get, when you put 0 in here at least, don't you now get x squared plus y squared equals 4? So you have basically told me that. Agreed? So this surface, this sphere, is cut in half. You're only going to look at the sphere above the z-axis, right? So that would generate that particular shape. I'm cool with that. Circle. And it's a whole circle. So in polar, it's going to be 0 to 1 and 0 to 2 pi. Well, I got this question. Suppose it was still the hemisphere, right? But suppose they cut it at z equals 1, right? So imagine the z was cut at z equals 1. So wouldn't the surface not be this guy right on the floor? Wouldn't it be like a piece of the top of a circle? Now, if z equals 1, wouldn't the projection on the floor become x squared plus y squared equal plus 1 squared equals 4? Wouldn't that become 3? So this would be the square root of 3. So I'd still get a circle, right? But a slightly smaller circle. Right, so if you cut it at z equals different levels, it's still going to go down as a circle on the floor to get us d. What else do I need? No, I think I got all the pieces. Again, I'm going to do polar based on D. And so the guy that we want is going to be an integral from 0 to 1, from 0 to 2 pi. And then it's going to be negative P dq by dx, negative Q, that's not a G, that's a G, a dg by dy, plus an R, and since I'm going polar, r dr d theta. And there is something I missed. I need my g of x. I need the equation of my surface, and I need it to be written as z equals, agreed? So if I rearrange this, and I know that it's the top half, that's why I can just put a plus there. Can you see the g of xy now? You see it was kind of hidden in the equation. Right, now we've got everything we need. So it's
Did
going to
the
be,
R value go from 0 to 2 instead of 0 to 1?
yes, it did.
Okay.
Okay, negative of this guy is negative y. If you differentiate this fella, I guess I'm going to have to call it 4 take away x squared, take away y squared to the half. If you differentiate this fella, you're going to get 1/2 that guy to the power of negative 1/2 times the derivative with respect to x, which is negative 2x. It doesn't matter how far to the left, I'm never going to have enough room to write these in one go. So next fella is negative q. There's p, there's q. So the negative of this gets me plus x times the derivative with respect to y, which looks very similar, except times negative 2y, plus an r. And in this case, it's plus 4 z's. And z is this guy. And everything then gets integrated eventually with respect to r and theta. This guy, this guy, this guy, and this guy, 2 pluses, I get 2, I don't get 2 anything. I get an xy with a 4 minus x squared minus y squared thing. And then I get this guy, who is minus xy, 4 minus x squared minus y squared to negative 1/2. Then I get this guy. And nobody noticed that that's 1/2. Just double check this. That guy gets killed off by that guy. And now I'm left with slowly but surely getting to the point where we can actually do this integral. Okay, all I've got is 4 minus x squared minus y squared, right? And I want that to be r or thetas. I'm pretty sure it's r's. What will 4 take away x squared, take away y squared get us?
Four minus r squared.
Correct. Now this is separable. So I'm going to do the integral from r equals 0 to r equals 2, 4r, 4 minus r squared to the half, that's the first guy, times theta equals 0 to theta equals 2 pi of 1 d theta. And this is where I'm going to stop here. That guy is easy, 2 pi. David, how about you? What technique will I use to integrate this fella here?
Use the
U sub, our favorite go-to technique, isn't it? The number of times you use sub is more than anything else, isn't it? That's the most common method that we deal with. Yeah.
I also noticed something when I decided because of that other one being weird to look at the next one. It also ends up adding a negative. The answer is negative for some reason.
And it does, you're right. Only this time, I'm happy about the negative because in the storyline that you can't see, it mentions that it was orientated downwards. So I'm assuming that orientated downwards means negative, orientated upwards means positive. That's what I'm hoping that means. In fact, it worked this time, so it's a good sign that that is what it means. Any questions about this particular subgroup of surface integrals, the ones they're calling fluxes? No. They're long, and I think that's the only 2 that I could find. Let's see if there's another one I just missed. No. Okay, put this over here. We're still working on surface integrals. This time I'm going to, where are we? Which one shall I pick? I need a u theta first, and then we'll do the conversion back. Where am I going for this? Oh, take it back. They're kind of mixed up, but I'm going to do 5, which is 1 more flux. I think these guys, the more practice, the better. In this one, the vector field is xy, yz, and zx. We are told that the surface is 4 minus x squared minus y squared, which is some type of parabola. Actually, I think it's a parabola that goes that way. The z-axis going up here. And we're using our surface with that parabola, and they're telling us the floor. So they're telling us that we're only going to be using the part of the parabola that is above this rectangle, well, actually this square. And they used the word upwards orientation, which means my answer should be positive. And good it is. So we should have all the pieces. There's my P, there's my Q, there's my R. That guy there is essentially g of xy. My region D isn't the whole thing. It's, can you imagine this little guy? And it's only the piece of the curve that's designed by that shape. So I'm not, well, I guess it would hit there. Eventually it would hit there. So it would look more like that. Oh God, forget trying to draw it. It's a surface nonetheless. So I should be able to get the flux. It's going to be the integral. Now, since these are numbers, then I actually know who D is. This is essentially, they've told me D. So I don't need to worry about what the projection of the surface onto the ground is or anything else. If you tell me who D is, I'll just use it. And then we're going to put in our other guys, which is going to be negative P dg by dx, negative Q dg dy, plus an R, and I'm pretty comfortable this is going to be a dx dy story, right? Put it over here, try and see if I can squeeze it all in. P is xy. And if you differentiate this with respect to x, you get negative 2x. Q is that guy. And if you differentiate this guy with respect to y, you get negative 2y. R is zx. Now, if you multiply this together, you multiply that together. I think they're separate things, so I should do it.
Should xy be negative?
Is there a negative somewhere that I misread?
The xy,
Oh, here.
because it should be negative p.
Yeah.
Okay.
So
Shouldn't
this is
that yx be yz?
yes. Anything else? Is that 101? Did I get that right? Yeah, I got that right. Okay, I got something. I'm trying to, I've got to be careful. My 2's look like z's, so that is a 2. So these two get me plus 2x squared y. This thing are both of those y's. Yeah, this is going to get me plus 2y squared z. And it looks like I also have a zx. Okay, looking good. Not wrong with that guy. This guy has to be turned into 2y squared and replaces z by this fella up here that you can't see anymore, which is 4, take away x squared, take away y squared. And a zx becomes the guy you can't see, which is this fella, times an x, and to be a dx dy crushed in there. Almost there. Two x squared y, that gets you 8y squared. That gets you negative 2x squared y squared. That guy gets you negative 2y to the 4. We got a plus, and we got, no we don't, we have a plus 4x, and we have an x cubed y squared with a crushed dx dy at the end. Do any of these things combine in any way? Okay, then I guess there was no point in doing that line. Would you agree you've just got a very big, ugly polynomial? Not variable, separable, but you could eventually, you get the answer. And according to what I've got here, at least for the numbers I'm using, it ends up being that guy. And positive, because positive orientation or upwards. If there's nothing wrong with that one, can we now say that we've had 3 shots at flux, so we're a little bit more used to the process. Now let's see what can jump about now. I wanted to do the ones that we did last time again. So let's see if I can find one that we haven't done. No, we've done the square root. I don't want to do square root. Could do that one. Not yet. No. Trying to find a suitable question is the problem. Done that one, done that one. Here we go. This will be our last question for today. Question 8. We're being asked to find a surface integral. This time x plus y plus z is our function. So it's a different type of question. S is a parallelogram with parametric equations, u plus v, u minus v, and z is 1 plus 2u plus v. And we're also told that u goes from 0 to 5 and that v goes from 0 to 1. And anything to do with positive or negative orientation, there is no mention on this question of either. So I'm going to assume that if you don't tell me anything that's positive, at least 50% of the time I'm going to be right. Right, now these guys involve a different formula. We need to find that guy, don't we? In fact, don't we have to turn everything into u's and v's? So our answer is going to look something like this. Instead of x plus y plus z, that's x, that's y, and that's z. You then multiply by that little guy. And this little guy is actually 2 by 2, which is fine. And then we can do a do u dv. And since these are numbers, I could just put in u equals 0 to u equals 5 and v equals 0 to v equals 1. So in a lot of ways, this is well on its way to being finished, right? Turn everything that says x, y, and z into the parametric equations u and v, parametric variables. Need to know what this guy is, but whatever he is, he goes here. Okay, so let me do that at the side. Ru is basically this vector, right? Differentiated with respect to u. So that's 1, 1, 2. Rv is this same vector, but differentiated with respect to v. 1, minus 1, 1. The cross product of those two vectors. So we do an I, a j, and a k. We put 1, 1, 2, 1, negative 1, 1. Let me do all that covering up stuff. 1, take away negative 2 gets me 3i. Minus 1, take away 2 gets me negative 1, so you add a j. And k, negative 1 take away 1 gets me negative 2, so I get negative 2k. So we have 3, 1, negative 2, and that's our cross product. We then find the magnitude of it, which is what the vertical lines are telling me. So that's going to be the square root of 3 squared plus 1 squared plus negative 2 squared, which is the square root of 14. I mean, there was a fair amount of work on the side, isn't there? But we're comfortable with the values I've got. This is your time to tell me that should be a +1 or whatever. Okay, we'll assume that that was done correctly. And then we'll continue with our thing. V equals 0 to V equals 1. U equals 0 to U equals 5. That guy's going to be the square root of 14. So I'm just going to stick it out there so it's out the road. And now I have a U, another U, and 2 more. So that gets me 4U. I have a V, take away V, they cancel out, +1, and add 1. How's that look? Du, dv. Everything look fine? Right. So I'm going to say ... and you finish off yourself. According to them, it's 115 halves the square root of 14. I'm glad that says square root of 14 because that's a good sign that I did this correct. That, I don't know. I'm assuming that's the ugly fraction you get out of that. It's hard to tell by just looking. And it is positive, so I got the sign right. Any questions before we call it a day? I think this is a good natural spot to finish. Right, last name and bye-bye. And why don't one of you go and figure out how you tell positive or negative orientation if they don't tell you? Because that's still bugging me. I'm going to see if I can find out how you tell positive and negative orientation as well. My gut feeling is it's something to do with those right-hand, left-hand rules that engineers use, but that's just a gut feeling. Bye-bye, and I will see you